let's just start with a little bit of a recap. So in the previous lesson, we were talking about calculating probabilities where we use the structure called a tree diagram. And all a tree diagram does is it shows us a way to figure out what are the favorable outcomes for a question and what are the possible outcomes. So all it's doing is it's helping us visualize these things. Now, in this particular question, this is the golden rule of probability. This is the equation that rules them all. Now, I want to know, can you find me, if you're given a bag with 2 sets of balls, so 2 sets, and you've got 12 red ones, 1, 2, 3, 4, 5, 6, 7, 8, 12, and you've got 5 blue, 1, 2, 3, 4, 5, and they're all mixed up, and you are picking from this, there's my hand, it's not a very good hand, but anyway, you're picking from this bag, and you take one out, we don't know what color it is, you then put it back, and then you pick a second one. Can you draw a tree diagram to represent the situation? And then can you work out the probability that both balls are red? Now, I want you to have a go at this from the beginning. And then if there are questions or comments, I would love to receive them from the students. But let's just see how it goes. We did a little bit of this in the last lesson, and so we can play around with this now. I'll give you one hint. Your first tree will branch into red and blue. Now, when you've completed this, just put done in the chat. So the chances of getting a red are 12 out of 17. And the chances of a blue are 5 out of 17. Now, that was our first go, but there's also a second one. Now, it says here that replaced, you put the ball back. So the first choice and the second time you choose it, they're independent of each other. They don't affect each other in any way because they're the same amount of balls. And so because you replace it back into the original, it's still going to be red 12 out of 17, blue 5 out of 17, and blue. And so what we do is we write the outcomes at the end of the branch and the probabilities on the branch. Now, what is the probability that both balls are red? Well, for both balls to be red, I would have to get a red on the first go and a red on the second go. What is that number going to be? The probability of getting a red followed by a red. Pop it in the chat there. So I think you are just going to go 12 over 17 times 12 over 17, which is equal to 144 over 289. And if you wanted to put it into decimal language, you would go 144 divided by 289, and that would give us 0.49826, and so on. Now, what's important to notice is that it's not a 1 in 4 chance of getting red. Even though there are only 4 possible outcomes, these outcomes are not equally likely. And so to get the probability of this outcome, you multiply along the branches. Now, what we're really doing with the tree diagram is we're using, in this case, we're using the independent events rule. Like when you draw something from a collection, and then you draw again, and essentially nothing is different when you start the drawing process. These events are independent. So we can just use the independence rule that says, well, what's the probability of getting red and red? It's just the probability of getting red the first time times the probability of getting red the second time. And so this is the formula that we're using to power our tree diagram. Give me a thumbs up if you followed that. Give me a thumbs down if you didn't. Just want to get a quick feel for the room. Okay. Now, I can see there are some students who still feel a bit confused. So let's go on to a second question where I actually give you the probability tree or the tree diagram. So this is the question. It says, a jar contains 7 red discs and 4 blue discs. 2 discs are selected and then replaced. This means the first disc is returned to the jar before the second disc is selected. Are the events independent? Why not? Yes, they are independent because the outcomes are the same. The outcomes you're choosing from are the same. But if I look at this tree diagram, I want you to work out the answers to these 4 questions here. So the first probability is the discs are 2 reds. And then the second one, I want you to give these ones a go. And I'm happy to answer questions as we go, but just start by asking which outcome would give you a redder than a red, and what do we think that probability would be? Okay, over to you guys. Let's see if you can use this type of question to help you. What do we think that pathway is going to be? I think it's just going to be that. Yeah. So the very first one is just going to be this branch, and I multiply the probabilities, and I get 49 out of 121. Let's try and do now. And if there are any questions, pop your hand up, and we can discuss what the next one is. Otherwise, keep going and do all 4. First disc is red, and the second is blue. Okay, yeah. So the second one is 28 out of 121. What is the third one going to be? Only one of the discs is red. So if you have two outcomes that are favorable, what you need to do is add those two probabilities together, because both of these outcomes are favorable outcomes. So they both count. So we know only one of the discs is red, is either going to be red, blue, or blue, red. Now you already know that the one branch is 28 out of 121. But now you also have a second branch, which is 28 out of 121, which you then have, if you put it in your calculator, you'll have 56 out of 121 for the third one. Okay, so when you have two branches, you have to add the probabilities together. Let's try and do the last one, number 4. At least one of the discs are red. At least one of the discs are red. Are one of the discs red in this path? Yes. In this path? Yes. What do you think the answer would be here? So if there are 3 branches, there should be 3 outcomes. So we already know what red is. We already know what that one is. And we already know what that one is. So there is an 86% or 86.77% chance that that you will get a red as one of your discs that you're drawing. Okay, so this is another type of exam question that we could have. Give me a thumbs up if you're following okay. Give me a thumbs down if you're not following the way that I'm doing these. Just want a quick reality check from the people of grade 11. Thanks, Nompolelo. Okay. Now, if you are feeling unsure, why did we add that? Oh, okay. Lorato has asked, why did we add that twice? We were trying to add, if you notice this branch will be 28 over 121, and this branch will also be 28 over 121. This branch would be 49 over 121. So we were just adding these 3 together, because the one that doesn't count is the BB, the blue. Okay, I can see quite a few students are still not quite there yet. So let me do another example like this before we move on. Let's do this one. So it says, 2 identical bags are filled with balls. There is bag A and bag B. Okay, so bag A contains 3 pink and 2 yellow. And bag B contains 5 pink and 4 yellow. It is equally likely that bag A or bag B is chosen. what does it mean if it's equally likely that bag A or bag B is chosen? If I had to draw it on a tree diagram, like bag A, bag B, what does it mean if it's equally likely either of these are chosen? Okay, it means that they're equally likely in terms of chance. They could be a half and a half, or 50% chance of either. Okay, now, each ball has an equal chance of being chosen from the bag. A bag is chosen at random. A ball is then chosen at random. What are the two color choices for bag A? What are the two color choices for bag A? If you look at the diagram, what do you think the two choices are? Yeah, it's just going to be yellow and pink, or pink and yellow. And what about the choices for bag B? What are the choices going to be there? Well, it's going to be the same. It's going to be yellow and pink. But what's different is the numbers are different in each of these bags. So if I have to ask you now, if you're in bag A, what is the probability of drawing a yellow ball? What's the probability of drawing a yellow ball? Yeah, it's just going to be 2 out of 5. What's the probability of getting a pink ball? No, it's going to be 3 out of 5. Okay, so you're just making your choices. Now, if for bag B, what's the probability of getting yellow in bag B? So in total here, there are 9. So there's a 4 in 9 chance of yellow. And for pink, what's the probability of pink in bag B? It's going to be 5 out of 9. So look at that. You just, in this situation, you have done your tree diagram. There's bag A and bag B. They're equally likely, 50%. And then the chance of getting yellow is this. Now, there are 4 outcomes, but they're not all equally likely. They differ. So let's do this one. What is, let's just skip 9.2. Let's do 9.3. What is the probability that a pink ball will be chosen? What is the probability that a pink ball will be chosen? Now, which of the pathways are relevant? And see if you can answer that question. What is the probability that a pink ball will be chosen? Yes. So it doesn't say about bags. It just says, and so ask yourself, which of the pathways end up with a pink ball being chosen? You could choose a pink ball from bag A, but you could also choose a pink ball from bag B. And both of these choices would be favorable outcomes. And all it said is, what is the probability of getting a pink ball? So I think we need to find the probability for each of these branches and add them together. So let's see what I get here. So you should get 26 out of 45. So there's a 26 out of 45 chance that you will get a pink ball when basically choosing a bag at random and then choosing a ball at random. Okay. Give me a thumbs up if that was okay. Give me a thumbs down if I lost you on that one. Okay. Now, what I want to move on to, a little bit of a preview before the break, and then we're going to move on to thing after that, is what happens if I don't put the balls back. So what we call the balls are, we're drawing without replacing. And I want us to have a little look at this one before we have our break. Now, if you do not replace the balls back in the bag, are the first and second draw still independent of each other? So the first time you draw and the second, it used to be that if you put it back, these two draws were independent. But if you don't put the ball that you chose back, are the first and the second draws independent? No. Yeah, they're not, because you change the number of balls in the container. And so when you change the number of balls, you change the odds. Okay, so let's do this one together. A bag contains 12 red and 5 blue. A ball is drawn at random and not replaced. Then another ball is drawn. What is the probability that both balls are red? Now, the important bit is it's different because it's not replaced. But on the first throw, what are my two choices? On the first choice, what are my two choices? So it's still going to be red or blue. Yes. So no problems there. On my second go, what are my choices going to be? Yep, nothing too exciting here, red or blue. Okay, so that's the same. What is the probability of getting a red on my first throw? What's that going to be? So I look here, 12 plus 5 is 17, so 12 out of 17. And the chances of getting blue are going to have to be 5 out of 17. Notice how together they add up to 1. Okay, here's where it gets a bit more exciting. If I choose a red, I've taken 1 out of the pack, and I used to have 17. How many are now left inside the bag if I've taken 1 out already? So I want to suggest that whenever you calculate going forward, all of these are going to be out of 16. Give me a thumbs up if you understand why on the second draw, if you've taken 1 out, your choice is always out of 16. Give me a thumbs up if you get that. It's very important. Okay. Now, if you drew red on the first choice, and you're drawing your second one and it's out of 16, how many possible reds do you still have that you could maybe choose? Well, you knocked off 1. There were 12, so that must be 11. Okay, but now let's pretend you got red on the first go, and now you want to know what's the probability of getting blue. You have 16 to choose from. How many of them could be blue? Okay, now the blues have not been affected because you chose a red in first. So this would be 5 out of 16 because you chose a red. So the number of blues in the box stayed the same. Give me a thumbs up if you understand why the blue stays the same at 5. Whereas the red had to go down by 1. So think about it. If you chose red, you've taken a red out of the pack. There were 12, so it has to go down to 11. But if you are talking about blues, you haven't affected the blues because you didn't choose a blue. Okay, let's do this next one here. If you chose a blue on the first round, how many reds are there left that you could choose out of the 16 that are left in the pack? Well, because you chose a blue, there's still going to be 12 reds left. And then if I go to the other branch, there's 16 left. You chose a blue on the first go. How many blues are left out of those 16? Well, you had 5. 5 minus 1 is going to be 4. Okay, so you have now learned how to do a tree diagram where the events are not independent. They depend on each other, but it's a very similar idea. Now, I want you to try and work out what is the probability that both balls are red. So if you take one out, it's a red, you put it aside, and then you choose the next one. What is the probability of that happening, of getting a red and then a red? What branch of the tree am I going to be dealing with? I think it has to be that branch. What are we going to get for our answer? So what I notice is I should get 33 out of 68. And so, yeah, that is how I would do it. So it's actually not so bad. When we call these dependent events or drawing without replacing, it's just the second throw that needs some adjustments. Okay. All right, everyone, we've been working for a while. I want you to turn on your cameras and I want you to stand up with me because we need a brain break. So on your feet, turn on those cameras. Let's see your happy faces. And let's just start by stretching up. Let your body feel free for a bit and shake out those arms. Shake out those arms. Shake out those legs. Let's do a little bit of twisting. And as you feel more relaxed, you can go further around. Okay, let's roll the shoulders. Roll them back. Roll them forward. Okay, let's do some triceps. And then let's do this one. Okay, and then let's shake it out. Okay, and then let's get our heart rates up. We want to do let's do some air skipping. And we're going to do 20 air skips in 3, 2, 1. Let's go. And that is today's exercise part of the brain break. Let's see if you guys can solve today's Maths 24 puzzles. So can you find 24 using these cards? I'll give you a moment while I put my top back on. All right. Who feels like they've got it? How would we get to 24? Okay, in Paul, so 8 minus 4 minus 1, which will give us 3. Yes. Well done. The red one is yours. Kitsaw has said that 2 times 7 is 14, and plus 2 times 5 is 10. Oh, Kitsaw, you nailed that one straight away. Well done. Anybody else agree, or has anybody else done the blue one? So Zuki has said 8 times 4 minus 1 times 8. Yes, Zuki, that's perfect. Well done. And Lorato has said 4 times 7, which gives me 28. And then you go minus 3 plus 1, which gives me 24. Yes, Lorato, you have absolutely smashed it. Okay, well, you guys are on fine form today for Maths 24. Oh, and I love this. Linda has found a different way. So 3 times 7 plus 4 minus 1. I love how there's so many ways to get to the answer. Well done, Linda. Okay, well, now that we've done our little brain break, I hope that you feel like you escaped for a little bit. But back to our tree diagrams for representing probability questions. Let's see if you can do this one. So, a little bit harder this time. Let's start with drawing a tree diagram to represent all the probabilities. So I want you to try and draw the diagram. It's got 3 parts now. And I want you to say done when you feel like you've done it. See if you can draw your own tree diagram here. So if there are any questions, you can pop your hand up and I will see if I can assist. Otherwise, just get drawing your diagram. Oh, Paul, that's so nice to hear. I'm so glad for your success. Mm. You know, often it just takes quite a couple of examples where you gradually increase the difficulty and it makes so Now, it seems like the second throw is the hardest one. So first, and then the second. Now, it must all be out of 20 because there were 21 to start with, and then you chose one. Now, I think that this has to be, because I chose white, this has to be 7, and then these ones remain the same. So it's only the white branch that gets affected because I chose a white branch here. Then here, that's going to be 8, 5, 7. And then over here, it is going to be, white is still going to be 8. This is going to be 6, and this is going to be 6. And another thing that you need to watch out for is that, can you see how these always, each branch adds up to 20 out of 20, like 7 plus 6 plus 7 gives you 20. So Timbaka, I'll do my best. So we're choosing between white balls, black balls, and green balls. So WBG. The first time we choose a ball, we write down its color and we put it to the side, which is why if we started out with 21 balls, on the second throw, all of our choices are out of 20. Okay, so the first thing is, give me a thumbs up, Timbaka, if you understand why it's out of 20 here. Are you okay with why it's out of 20 on the second throw when it's out of 21 on the first choice? Okay, now, if you've chosen white on the first go, there's one less white ball in play. There were 8 white balls to start with, but now in the second choice, there's 7. But when you go to the other branch, well, if you chose white to start with, you haven't affected blue and green, or black and green, sorry. So they stay the same. It's 6 out of 20 and 7 out of 20. Whereas on this branch, you affect the black one. So there's 8 white balls. It's still the same because you chose a black. But then on the black line, it's 6 minus 1 to give you 5. So that's kind of what this is doing. Now, I want to know from the students of the room, what is the probability that I choose a green ball on my first go, I put it to the side, and then I choose a green one on my second go? Pleasure, pleasure, pleasure. I like to know, what pathway am I on? So both balls are green, would have to be that pathway. To me, it looks like that. So what am I going to get for that? Well, my first choice, 7 out of 21, and then 6 over 20. So what does my calculator say? We are going to get 1 out of 10, or a 10% chance. So there's a 10% chance that both balls will be green when we draw without replacing. Okay, so that's not too bad. Now, a little bit harder one. What is the probability that 2 balls are white and green in any order? See if you can work out this one. So which pathways are favorable for this question, and what are the probabilities for those outcomes together? See if you can do 4.2.3 for me. So I guess I should make sure my pathways are correct. Oopsie daisy. White and green. White and green. Well, that could be white and green. And And that could be, so basically what I'm saying is, what is the probability of getting WG or GW? And I'm going to add them. So I'm going to get 8 out of 21 times 7/20, which is that branch, plus 7/21 times 8 out of 20. Now, what is my grand total going to be? And my calculator is telling me 4 out of 15, or it's just less than, if you put it in decimals, 0.26, so about 26.6%, or I'll leave it as that. So like, look, it is possible. Okay, you're doing nicely, everyone. So is the diagram always going to end on the second branch? It's unlikely they would want to do a third branch because it just gets a bit out of hand. You can imagine it's not impossible, but it's very unlikely. Okay. Let's do an old exam question. I want you to do this by yourself. Here you can see it's from an old exam. See if you can answer this question by yourself. I'm not going to say anything. I'll just answer if people say, if they say that they want some assistance. But I think you can fly solo on this. So I've drawn the tree diagram for you. Sometimes if they say they want the explicit outcomes, you can, I don't think this is really necessary, but if you really want to, you can show that there are 4 specific outcomes, but that's generally assumed on the drawing. What I want to know now is determine the probability of first taking a red marble and then taking a blue marble in that order. So red marble and then taking a blue marble in that order. So it feels to me it has to be that outcome. And that one is going to be 2/5 times 3/4, which is 6 out of 10, 6 out of 20 rather. So 6 out of 20 and 3 out of 10, or 30% chance. Cool, no, that wasn't so bad, hey? That was from a past exam paper. So isn't the total of the second branch still 5 because the balls were put back inside? No, so this says put aside, not, so when they say put aside, it means that it's taken out the bag and put to the side. So it's not, yeah, no problem. But it's a good point, watch out. If they had said put back in, then it would be out of 5, not out of 4. And that's an easy mistake to make. Okay. Let us do another sort of past exam paper, but where it's a little bit more, it's like phrased in a different way. So we'll probably finish off with this one. So I want you to try and draw a tree diagram for this situation. And it's the same idea, it's just applied in a slightly different way. See if you can do this question. What do we think are the first 2 possible outcomes? Yep. It's either raining or it's not raining. Yeah. Exactly, Linda. I agree. So it's raining or it's not raining. Now, the probability it will rain on a given day is 63%, or we can say 0.63. What do we think is the probability it will not rain on a given day? It feels like these are what we call complementary events. So that means this has to be 0.37. Okay, so that is our first choice for the day. Whether or not it'll rain or not rain. Well, it's not really a choice, hey? It's like something that's uncertain. Now, it says here that a child has a 12% chance of falling. But now, before we even think about this, what do we think are the 2 options that we're going to be splitting up for the second choice or the second event? Because that's a little bit sneaky in this question. Like, what are the 2 choices? So either it rains, to not so much dry or wet, it's going to be whether or not you fall or you no fall or don't fall. And this one can be, because you can still fall when it's not. So the question has been asked, how did I get 0.37? Well, because there's 100% chance that it either rains or it doesn't rain. If this one is 63%, I just went 100% or 1 minus 0.63 to get my 0.37. Okay, now it says here, a child has a 12% chance of falling in dry weather. Now it's going to be dry when there's no rain. So maybe we could say this one is the same as dry, and this is the same as not dry. These are the same thing. Now, a child has a 12% chance of falling in dry weather. So I'm going to make this 0.12. What do we think has to be on the other branch? So I think that on the other branch, it's going to be 0.88 because you either fall or you don't fall. And then it says it's 3 times more likely you will fall in wet weather. So what do you think the probability is on this branch over here? If it's 3 times more likely. So this is going to be 0.36. Yeah. And then what is the probability that you will not fall in rainy weather? So this is going to be 0.64. Okay. So it says here, let's just finish with the last question we'll do today is this 3.2. We're not going to go any further. What is the probability that a child will not fall on any given day? So what is the probability that a child will not fall on any given day? So think about which pathways are relevant and how would you work out the probabilities? I think on any given day, not falling, or the probability of not falling on, I think it has to be those 2 branches. So how would we work out the probability of those 2 outcomes? So, Karabo, what we did was we went from the 0.12, and in the question it said it's 3 times more likely in wet weather. So when we went up to the wet weather or the rainy weather, we went from 0.12 to 0.36 by timesing by 3. And then we said together these need to add up to 1. So if you go 1 minus 0.36, you get that. Now it says here, what is the probability that a child will not fall on any given day? Well, all I need to do is calculate the probability of these 2 things, which I'm going to need my calculator with. So 0.63 times 4 plus 0.37. And you should get 0.7288. So there's a 72.88% chance that you will not fall on any type of day. Okay, here if you could put the link to the quiz, not the quiz, the poll in the chat. Thank you, everyone. I hope you had a good lesson, that you learned a lot. It did look like you guys were understanding plenty. And I think it's just practice like anything. And hopefully you have a good base from which to practice even more now. Let me know in the poll how you felt about the speed of the lesson today. Tebogo, I will finish it off in the next. I think we've run out of time now, and I think a lot of people are leaving, so I'll finish it off in the next lesson. Where's the probability that a child will fall in dry weather? Okay, that basically, if it's dry weather, it would have to be, it assumes that there's dry weather. So then it's just going to be, if it is dry, fall, it's just going to be 12%. So that's just going to be a 12% chance, because you're just saying, I've already got this. I know this is true. So therefore that must be 12%. Okay, so I hope that helps.